anyway. So first property is basically the definition of a log in action. So the log a of 1 is 0. Okay, you ought to know that. The reason this works is if you're not sure what this is worth, so you could write it this way: the log a of 1, and then we'll just solve this for the log a of 1. So what's the definition that I can use here would be a to the power of y. So a to the power of y equals 1. There's only one answer that can work here. Not 1, because a to the first would be 1. It's going to have to be 0. In case you're not sure that that will work, could I write 1 as a to the power of 0? 0 on anything gives you a 1, right? So this only works when y equals 0. So we just proved that this has to be true. Okay, this would be one of the properties you ought to be able to prove, and this is it. This is the proof, what I just showed you. Does anybody have any questions on that one? Okay, the next one, and this one goes with this, so we'll do this side by side a little bit. The log a of...
Your attention please, Bethany Curl, please report to the Education's office. Bethany Curl.
The log a of a equals 1. We can prove that the same way. You would write y equals the log a of a, and then we use the definition of what a log is. So a to the power of y is going to be equal to a. What exponent can I put on this a here to make this work? It's a 1, right? So an a by itself would be an a to the first, so this is true when y equals 1. So these are two properties that you ought to be able to prove. Okay, so they're not quite the same, but they are very similar in the way that you prove them. We weren't here yesterday, but a log is just, it's a question and it's asking you for an exponent. So what exponent do I need to stick on a number to make something work? So for example, the log base 10 of 100, we'll make it 1,000, unless you think it always comes out with the same number. Okay, so I'm looking for the exponent that I need to stick on 10, so this is the question mark, to make this worth 1,000. So, it's not 2, because 100 squared would be 100, right? It's not 2, because 100 squared would be 100, or 10 squared would be only 100. So it would be 3, because 1,000 is 10 cubed. So this is what a log is. It's just a question. Okay? We're good? So I'm going to clear it. Okay. Alright, next property. This one you are not going to have to prove, because the proof is different than being able to answer it sort of by seeing patterns. But this is your Bellwork one, isn't it? A log a of m, for example. And I did it with 5, but if I have 10 log 10 of 100, your answer here has to be what? Not 2. This one was your Bellwork. Your exponential base and your logarithmic base match, so since they're both 10, your answer here is going to be that 100. Okay, so the a log a of m is always whatever that m is, by definition. That one is a little bit harder to prove, so we don't have to prove it, but you need to know it, but you can reason your way through it. Okay, the reason for that being because you can split this into its exponential part, which is log 10 of 100, which we know is 2, and that means that you can put this 2 up here, and 10 squared gives you 100 back. So it's not really proving it, it's just showing that it would work. It's different from proving it. But we need to be able to know that. Okay, so that's your Bellwork sort of revisited. It's the same one. I just gave you different numbers on this one. Can I erase this? Yes? See in the back, people still copying. Okay, next rule that you should be familiar with is this. the log base a of a to the r is equal to r. That's the one that I showed you yesterday. You won't remember that, so we'll redo this sort in a different version. So if I, for example, wrote this down, log 7 of 7 squared, what's my answer going to be? So I'm going to introduce a variable here. Like, I don't know what this is, so I'm going to put an x there. It's going to be what? X equals 2. That would be right, because you can use the definition of your log, which is that 7 to whatever exponent we're looking for, that's your x, has to be equal to 7 squared. So x ends up being, has to be 2. So you don't have to keep doing this. Whenever you have the bases match, if this base matches that base, and there's an exponent on it, you just get that number. You get 2 in this case. So if this had been a 21, we would have said x is 21. Okay. Not to prove again, so I'm not going to ask you to prove this. Even though it's simple, it's sort of awkward to prove it. But that's a rule that you ought to be familiar with. Alright. The next two you're going to have to prove, and these are the sort of the more challenging proofs. So this is the second and the third proof, and that deals with the following statement. That would be the log base a, so any base you want, of two quantities that are being multiplied is going to equal the log base a of m plus the log base a of n. Okay, to prove that, we have to rework this a little bit. So let's let capital A stand for the log base a of m. If that's true, then a to the power of capital A has to equal m. Is that fair to say?
Yes.
By definition, a to this exponent is the number we're looking for. So I'm just using the definition of what a logarithmic function is, which is the inverse of the exponential that goes with it. Okay. I'm going to do the same thing for the other one, but I'm going to call it capital B. So capital B stands for the log base a of n, which then has to mean that little a to the power of b is equal to n. So I haven't proven anything yet, I just need this to be able to prove this. And now it's a matter of filling things in and cleaning it up a little bit, which is a little awkward, but once you do it once or twice, it'll hopefully make sense. Can't find my cursor. Okay. So the log a of m times n can be rewritten by plugging in those values that I just wrote. So how much is m worth? Well, m is worth a to the power of capital A. You guys see how I'm just plugging this one in here? I know that m is a to the 8th power, so I'm just plugging it in. Yeah, well, I have to have a's in here so that it works. I could do it all with c's and d's, but I have to have this, sort of the same letter. The same thing goes on over here. This n is actually a to the power of b. So you can simplify this. You have the same base here and exponents here, so you can simplify that into what? What do you do with your exponents when you multiply? You add them. So I can rewrite this as a plus b. Yes, I know. This is why at some point you have to do this a couple of times. Okay. We just discussed the rule that if you have a base and this exponential base matches that base and you have an exponent here, this exponent comes out, right? Like what I have here is another version of this. The log a of a to the power of r equals r. Well, that's what I have here. Log a of a is a plus b. So this has to come out as a plus b. Okay? We just proved that that rule works. Well, actually we didn't prove it, but since that rule has been proven, we can use it. And how much is A worth? Way up here, A is what? Log A of M. So A is log A of M, and B is log A of N. So I just proved that this works. Because I started out on the left side. I started out here, and I show through manipulating all this mess that it comes out like this. So that's what the rule says. Okay? Alright. We'll just re-clear the plates. Okay. Next rule is tied to that, and that would be the rule that you need to know what happens when you divide inside your log. What do you get then? Keep in mind that logs are like exponents, right? And we just saw that when you multiply things, what do you do with your exponents? You add. When you divide things, what do you do with your exponents? So intuitively, hopefully, you understand that this has to sort of happen here. We should be subtracting our exponents because logs are exponents. So I'm going to prove this rule. Starts the same way. You have to define that this works. So we're going to call capital A is log A of M. That means I can rewrite this as A to that power is equal to M. And then I do the same thing with the second one. So this is capital B is log A of N, so that we can write A to the nth power is equal to B. Sorry, let me erase that. Thank you. What would it be, Alyssa? You're right. So A to the power of B is equal to N. Thank you. Alright. Same thing. Just plug it in. So we have log A of capital M divided by N. We're going to plug in what M and N are. So log A of M is worth A to the power of A, and N was worth A to the power of B. What do you do with your exponents when you divide? You guys just told me that. You subtract, right? Log A of A to the power of A minus B. If you can do the first, this one's not too bad. You just got to wrap your mind around the first one. This follows exactly the same pattern. Okay, then you get your rule, which says that if this base and that base matches, you just get A minus B here. And you finish by stating that A is worth, A is actually the log A of M.
What kind of A?
Log. Capital A is worth, up here we wrote that capital A is log A of M. And capital B was worth log A of N. And that completes your proof. And you ought to be able to do that. Okay? So there are 3 proofs that I'm going to expect you to be able to do. These, then this is it. And I do have to show you a couple more rules that you're familiar with. And then I'll give you a couple examples how they work. We're good? Can I erase this?